Okay, moving on to chapter 5 in our textbook, Monte Carlo methods for reinforcement learning. We'll start doing some online learning through interaction with the environment. And specifically, we're going to cover a simple set of algorithms, the most straightforward way to do reinforcement learning. And these are known as Monte Carlo methods, and we'll continue from there. Okay, we'll start the more easier algorithms and build our way upwards. So this is the general high-level structure of our course. So today we're going to solve MDPs, not offline. So we're going to start solving them online using Monte Carlo approaches. We'll still assume tabular settings, but later on we'll see how we can use actually Monte Carlo approaches to do to combine these with policy gradient approaches and use them together with policy approximations. But we'll do that later on, don't worry about that for now. So just as a reminder, we are solving or assuming some underlying Markov decision process that we would like to solve. And by solving, I mean to compute the optimal policy for. So the MDP is composed of a set of states, S, a set of actions, A, some model, which defines the probability from transitioning from each state to a different state given a specific action. Also a reward function, an immediate reward function, which is a function of the state, an action, and possibly the next state, right? Also, we usually include a discount factor in our MDP. And as before, we are looking for the best policy, the optimal policy, pi star. How to act in each one of our states. What's the best way to act in each one of our states. But now we add a new twist. We don't assume to know the model or the reward function, right? So, meaning that we cannot predict the action's outcome. We cannot predict what would be the reward that we're going to observe, and we cannot predict the next state that we're going to arrive at. So instead, we're going to interact with the environment in order to learn the optimal policy. And this is what defines offline learning versus online learning. Okay, now instead of trying to imagine what will happen if we take action in different states, or to assume to know what's the distribution of next states or distribution of reward, we'll actually have to try performing a specific action in a specific state and observe the outcome. By the way, there might be a distribution over the outcomes, but we will only be able to observe one single outcome, right? That depends on, well, the outcome that we sample from the environment. As I said before, today we're going to discuss Monte Carlo methods. Monte Carlo methods are actually broader than reinforcement learning. These are general methods that are used throughout in various science disciplines. So this is a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. The underlying concept here is to obtain unbiased samples from a complex or unknown distribution through random processes. These approaches are often used in physical and mathematical problems and are most useful when it is difficult or impossible to compute a solution analytically. So you can find these methods, or they're often applied in weather prediction, computational biology, computer graphics, finance and businesses, sports game predictions, and more. So for instance, right, if you have a model of a sport game outcome, let's say that you're in a gambling company or a bookie, right? And you have to decide what's the probability of each, the winning probability for each one of the teams. And you have different factors that go into a very complex simulator that can simulate the full game and then predict some outcome. But the process is so complicated that it cannot be represented in a single function and then optimized using known optimization techniques. Or maybe it's non-convex, NP-hard, anything like that. So in the Monte Carlo approach, what you're going to do is you're going to simulate a game and observe the outcome. And of course now each time you simulate the game, you'll see a different outcome. But now you simulate it a million times and you see, okay, 60% of the time you actually team A1 and 40% of the time team B1, and now you have a distribution, a winning distribution, right? Over the, what is the probability? You have an assessment of the probability that team A will win. Okay, so that's an example of a Monte Carlo approach. And so now we can adopt this approach for reinforcement learning, specifically for value-based learning, right? For instance, we can learn an unbiased evaluation of the Q value of the action values, or maybe the state values. We can do it in a similar way. But as we said before, we'll usually try, unless we have a very good reason to learn a state value, we'll actually try to learn Q values because they also help us. They imply a specific policy, but it's much easier to extract the policy from Q value. So how can we use this approach to learn Q values? In a straightforward way, right? We experience the world through episodes, so we start from some initial state, and we choose an action following a specific policy, right? The policy that we'd like to compute the Q values for. It can be, by the way, a soft policy. It can be a policy with a distribution over the actions. That's also fine. That's a valid policy. And so we observe the initial state, or we're initialized in a specific state. We choose a specific action, A0, observe a reward because we interact with the environment. So we observe the reward. Doesn't require us to know the reward function, right? It might be, the reward function might be very noisy, but it will require us to be able to observe a reward that is assumed to be sampled from the reward function, even if it is unknown. And we arrive at the next state. Again, we don't know the distribution over the possible next state. We don't know the transition function, but when we interact with the environment, we arrive at some next state, right? And at that next state, we take an action, observe reward, and so on until we finish an episode. Once we do that, we can estimate the Q value by just summing all of the reward and the discounted sum of reward, our G, capital G value, as we defined it in the last class, in the last lecture. However, the Q values are not exactly a single sample of observed discounted rewards, right? Sum of discounted reward, because the G sampling might be noisy. But if we do it over and over again, we know that it will converge, right? It's how we define expected values, or empirical expected value, as the sum of samples over an infinite at the limit, right? So if we sample sufficient enough capital G values, we can take the average of those, and this is an unbiased estimation. It is an unbiased estimation in any case. At the limit, it will be exactly the correct Q value, right? The correct Q pi value. And in any case, over time, the values at the limit, they will converge on the true Q value. Okay, so let's see an example. Let's say that we have a very simple grid environment. And we have some input policy pi that we would like to evaluate, or we would like to compute the Q value for some policy pi. And let's say that our policy is given here. So these are the arrows. Can you see? Yeah, see the arrow? So these arrows are our policy, and state A and state D, here and here, are terminal states. So the only action available from there is X, let's say, and then you get the reward. I don't know which reward, right? So the reward function is now unknown. But these are terminal states that yield some reward. Let's assume a discount factor of 1, so no discounting for this case. And this is fine because, as you can see, we won't spend forever in the environment. This is a bounded episode. So in this case, it will be fine to have a discount factor of 1. And now we would like to estimate our Q values without knowing the transition probabilities and without knowing the reward function. So what we do, we're going to sample some transitions in our environment, some episodes in the environment. And let's say that the first time we interact with the environment, we start at state B. State B right here. Okay, so we start at state B. We performed action east. This is one of the actions that we can take. We arrived at state C, and we observed an immediate reward of -1. From state C, we applied action east, and okay, action east is I'm just following the policy, right? So we're following the policy that's given to us. We apply action east, and we arrived at state D, and observed an immediate reward of -1. At state D, we can only perform one action, which is action exit. And we terminated the episode and observed an immediate reward of +10. Okay? And we continue, because as I said previously, this domain is non-stationary, it's highly stochastic, so we'll have to sample several. So these values are not sufficient in order to learn the Q values for all of these states, for state B east, for state action pairs B east, C east, and D exit. Right? We have to perform the same, or sample the same state and action several times in order to be confident about the values. So let's say that in episode number 2, again, we started at state B, performed action east, arrived at state C, and observed -1. From state C, oh, it's exactly the same, right? Okay, so episode T is exactly the same as episode 1, but still it doesn't mean that this is what's always going to happen. So let's continue. In episode E, oh, we started in a different location. So in episode 3, our agent actually was initialized, right? So something in the environment caused it to start at state E. We followed our policy to state north, and performed action north and arrived at state C. At C, again, we performed east, arrived at D, and continued as before in episode 1 and 2. Let's see what happened in episode 4. At episode 4, we started at E, north, arrived at C. From C, we performed east.
I think that should be north.
Sorry?
It'll be action north. I think it's written wrong. From C, we go north to A.
No. So from C, we have a very specific policy that we're following. At state C, our input policy tells us perform action east. Okay, we cannot change that. We're evaluating a very specific policy. So at state C, we perform action east. However, for some reason, we actually found ourselves at state A. Okay? And from state A, we performed action exit and observed an immediate reward of -10. Okay, so now let's try to compute the Q values based on these episodes, on these samples, right? So for each state and action pair, we simply compute the average outcome that we saw from that point onwards towards the end, right? So let's, for instance, start from state B. So state B, we always performed action east. So what is the Q value for B east? Actually, let's do the state value. Okay, so we have a set policy, a deterministic policy. So the state values would be the same. Let's do this for simplicity. So what is the V of B? V of B based on Monte Carlo estimation.
Given the first episode?
No, given all episodes.
Given all episodes.
Right, so let's see. So at episode 1, we saw 8, right? Sum of reward of 8. Again, we use a discount of 1 just for simplicity. In episode 2, starting from B, we saw a sum of reward of 8. And episode 3 and episode 4, we never saw state B. Okay? So the state value estimation is the average G, capital G that we saw, which is 8. What about state C? V of C. Let's see. So
9.
in episode 1, we saw 9. In episode 2 we saw 9. In episode 3 we saw 9. And in episode 4 we saw minus 11. What's the average?
18 minus 2, 16, 4. 4.
4? Okay, I trust you. 4. Oops. And we do the same computation for all of them, okay? And once we do that, we find the following values. Okay, and again, please feel free to check my values. And as before, if you catch a mistake in my computation, you get a +1 in your final grade. And so now we have some Q evaluation based on our specific policy and based on Monte Carlo sampling, right? Hopefully this is straightforward. Okay, so this is a nice approach. Let's see what might be some issues. What are the pros and cons for this for a Monte Carlo evaluation approach? So first of all, what's good about direct evaluation? First of all, it's very easy to understand, right? Hopefully everyone understood how we did these computations. Secondly, it doesn't require any knowledge of the model, so this is relevant for online optimization and reinforcement learning. Thirdly, it converges to the true expected value, so all of our estimations are unbiased, right? So this is each trajectory, each G estimation, a G sample, capital G, sampling of capital G, is coming from the true distribution. It is unbiased, right? So eventually, it will converge to the true values, what we care about. What's bad about this? First of all, it wastes information about transition probabilities. And we'll see this in a second. I'll show you some computation that doesn't make sense. Or that you'll be able to see that we have some more information here that we're probably ignoring, that we could use. Secondly, each state must be learned separately. So we cannot learn some connection, or we cannot generalize our knowledge between neighboring or similar states. Right, so it might take a long time to learn. Right, and so here's an example of that shows us that we're probably missing some information. So let's look at state B and state E. Both state B and state E, in all of the episodes that we saw 2 episodes starting at state B and 2 episodes starting at state E. Both of them, for both state B and state E, all of the episodes actually resulted, we performed action north in E and east in B. And in all of the episodes, both of these transitions resulted in state C, right? Arrived at state C. So it seemed like, from our episodes, it seems like the transition probabilities from both state B and state E are the same, and both lead to state C. More than that, they both yielded the same immediate reward, right, of -1. So the transition from B to C and from E to C seem to be exactly the same from the episodes that we observed. However, the state value for B and E are very different, right? One has +8 and the other has -2. How can that be? Right? How can that be the case? And if you remember, that's because one time that we started at state E and arrived at state C, we didn't get to state D. I don't know, we tried to go east, but we slipped and got to state A. But that's not dependent on where we started from. Because of what property?
The Markovian.
The Markovian property, correct. So, being at C, once we're at C, it doesn't matter how we got to C, right? The expected sum of rewards from being at C is, well, according to what we saw so far, is +4. So it can't be, based on the knowledge that we saw so far, that B and E are different. Okay, so this is just an example where a Monte Carlo approach might miss some information. And we'll get back to that, and I'll show you some. I'll show you some ways to address that, right? Some ways that are considered low variance, so we won't have these noisy estimations like we have here, but these introduce bias. Bias meaning that they introduce the samples, the update samples that we'll use in those approaches are not necessarily coming from the true distribution that we're trying to evaluate. So they introduce some bias away from the true distribution that we're trying to estimate. And this trade-off between bias and variance is something that we see across machine learning in general, supervised learning, unsupervised, and reinforcement learning. And this is something that we'll also need to balance in these cases, in reinforcement learning, and we'll discuss it actually. We'll discuss it several times, right, moving forward.